So what you're probably more familiar with in terms of temperature is you've probably heard about Celsius before. That is the more commonly used form of the scale of temperature that you're probably used to. It's used a lot in science, and most of the things I did as a scientist, temperature was given in terms of Celsius. So Celsius degrees are the same magnitude as those of Kelvin, but the scales place their zeros in different places. So for example, water freezes at 0 degrees Celsius or 273.15 Kelvin. It boils at 373.15 Kelvin or 100 degrees Celsius. And so we're used to seeing temperature in Celsius, knowing the boiling point of water and the freezing point of water in Celsius. And converting between Celsius and Kelvin is very simple, and we'll talk about that in just a moment. The unit for time in the SI system is a second. Of course, everybody has a concept of how long a second is. It's very short. Smaller and larger time intervals can be expressed and used, for example, hours, days, years, months, etc. So, in terms of volume, generally we use the liter. That is our base unit for volume. Another way of representing volume is the cubic meter. Okay, and this is, of course, only useful if you have a substance that is in the form of a cube. Other units for volume are the liter and the milliliter, and if you look at graduated cylinders in the lab, they are graduated using the unit liters and milliliters. Okay, but you can also use a cubic decimeter or a cubic centimeter. So you're probably used to hearing about a cubic centimeter or a cc. A cc is a cubic centimeter, and so it's used a lot in medicine. Whenever you give you a shot, it's 5 cc's, that's 5 cubic centimeters. So a cubic centimeter is also equal to 1 milliliter. So if I gave you a shot of 5 cc's of a substance, then that's 5 milliliters of a substance. So if we look at shape of maybe if we have a cube and we break it apart into little pieces, okay, and looking at the size of a cubic centimeter or 1 milliliter, and comparing that to the size of a dime. Well, here the diameter of a dime is 1.8 centimeters, and the one side of a cubic centimeter is 1 centimeter. So the size of a dime is almost twice in diameter as the size of a cubic centimeter. All right, when we talk about density is defined as the mass per unit volume. And so the standard units for density for the SI system is mass is in kilograms, volume is in cubic meters. But in chemistry, normally kilogram, like I said earlier, is a very large unit. We normally use grams for when we're representing mass, and meter is a very long distance as well. We normally use cubic centimeters. Okay, so you'll normally see density values of different substances in using the units in grams per cubic centimeter or grams per milliliter. For gases, grams per liter are common because with gases, usually the volume of the gas we're dealing with is larger than the volume of liquids or solids that we use too. So next section here, we're talking about differences, being able to distinguish difference between accuracy and precision, distinguish between exact and certain numbers, correctly represent uncertainty in quantities using significant figures, and apply proper rounding rules to computed quantities. So counting is a way you can measure something and it's free from uncertainty. So if I count 5 apples, I have exactly 5 apples. There's no uncertainty in that value. However, when you're measuring something with a tool in the lab, it may not be exactly an exact number, and I'll explain why. So you're used to numbers telling you exactly what they mean. Like 1 foot is exactly 12 inches. 1 inch is exactly 2.54 centimeters, etc. But when you're taking measurements using a tool, some of the numbers are not going to be exact. So there are limitations with every tool you use. Okay. So when you're using a tool to measure something, that number must be reported in a way to indicate its uncertainty. So in general, when we record a measurement in the lab, you have to add a degree, your estimate of uncertainty, okay, in terms of a digit. Okay, so for example, here is a graduated cylinder. And notice that here with the graduated cylinders, we're measuring the volume of this liquid. And so if you look at how many hash marks you have between here, for example, the 10 and the 15, well, there are 1, 2, 3, 4. There are basically 5. There are 4 hash marks, but there are 5 spaces, right? So every hash mark represents 1 milliliter. So this is 10 milliliters. This is 11, 12, 13, 14, 15, etc. So here, when we're looking at the volume of this sample, we notice that the meniscus, which is this concave shape here of the water, okay, the way you measure the volume using a graduated cylinder is you're going to look at the value at the bottom of the meniscus, right where it goes at its lowest point here, okay? And so I know that I have over 21 milliliters here, but notice that the volume is in between the 2 hash marks. Okay, it's not going to be perfectly 21 or 22 milliliters. It's somewhere in between. Okay, so how much water do we have in this graduated cylinder? So somebody may say, oh, you have 21.6. Somebody may say it's 21.7, 21.5. So the 2 and the 1 are certain, right? We definitely know you have at least 21 milliliters in this graduated cylinder. But because the water is in between the hash marks, you have to have there's a bit of uncertainty as to how much you really have. So that last digit is your estimated digit. Okay, so the 6 here is the estimated. Here it says that the volume seems to be 21.6 milliliters. But if your lab partner says, I think it's 21.5 milliliters, that's fine, because again, that last digit is it's an uncertain digit because it's basically an estimated digit. Okay, you're estimating between the hash marks. Now, how can you improve this? Well, if I had a graduated cylinder that had hash marks in between the major hash marks, that graduated cylinder would be better to use because it's going to give me more information. Then I could extend my value. Instead of reporting it to 1 decimal place, I can report it to 2. Okay, so you're always going to include an estimated digit in our measured numbers. And so when we have our second lab, we're going to be using graduated cylinders, and you're going to be doing a lot of measurements, and you're going to have to report your values using the proper number of estimated digits. There's always 1 estimated digit, so you always go one beyond what you can actually measure from the hash marks on the piece of equipment. So all the digits in a measurement include the uncertain last digits, and so we have to learn the rules, what's called significant figures or significant digits. These are basically what these values are telling you is, if it's a significant figure, it's telling you that the numbers that are there are known. Okay, so for example, some instrumentation in the lab, for example, if we said that the volume was 21.58, that would not be correct, because we can't really, there are only 1 set of hash marks on that graduated cylinder. We really can't say that we can use more digits past 1 decimal place because of the limitation of the tool. Okay, so significant figures, what it does is once you learn the rules, when you're in the lab and you're reporting your data, you can't report data that extends beyond the capability of your measuring tool. So for example, if I weighed myself at home, my scale goes to 1 decimal place. So if I tell you today I weighed 100.357 pounds, you know, unless I paid a lot of money for a scale that, you know, gave me that many decimal places, which I don't have a scale that will do that. It will only go to 1 decimal place. So, you know, that saying that that was my weight would not be correct. Okay, it's not very truthful. And so, when you're, you know, producing scientific data, you have to report your numbers and also report the level of your precision using your instrument. And so you have to know the rules of significant figures. So we're going to learn how to figure out how many significant figures there are. So in this case, for example, there are 3 significant figures for our data that we can report if we wanted to report it in a scientific journal. So we have to know how many significant figures there are in a measurement reported by someone else that tells us the level of accuracy in their measurements. All right, so here are some of the rules for significant figures. So the first rule, numbers that are always significant are non-zero digits. So here we have 135. So how many significant figures do we have? So the 1, the 3, and the 5 are non-zero digits, so they're all significant. So that means I have 3 significant figures here. Captive zeros. I call these sandwich zeros. So if you have a 0 sandwiched in between 2 non-zero digits, that 0 is significant. So a captive 0 or a sandwich 0 is always significant. Trailing zeros. So when you have a trailing 0 that's to the right of the decimal place, it is significant. But if you have a trailing 0 to the left, it's not. So here we have a trailing 0. Okay, it's a 0 that is happening after non-zero digits. It's to the right of the decimal place, so this 0 is significant. Okay, these zeros are not, and I'll explain that later. They're referred to as leading zeros. All right, trailing zeros are also significant when in scientific notation. So here we have a number written in scientific notation. Here we see trailing zeros here. They're all significant because written in scientific notation, if they were not, you wouldn't see it. You would see, if like it only had 1, it would be 1 times 10 to the third. If there were 2, it would be 1.0 times 10 to the third. If it were 3, 1.00 times 10 to the third. Here we see all of these zeros are significant because they're written out. All right, leading numbers are always not significant. So, or these numbers are not always significant. Leading zeros. So, what is a leading 0? Well, if you're leading someone, you're in front of someone, right? So a leading 0 is a 0 that's in front of non-zero digits. And so these are referred to as leading zeros. This example here has 3 significant figures, the 1, the 2, and the 0 here. This is a trailing 0 to the right of the decimal place. Leading zeros are not significant. Trailing zeros are not significant if they are to the left of the decimal place. So here we have 10,000, the number 10,000. Okay, you don't see a decimal place there, but if you were to put one in on this number, it would occur at the very end of the number, right? So 10,000 point whatever. So if they're to the left of the decimal place, they're not significant. So that means all these zeros here are not significant. They are trailing zeros, so there's only 1 significant figure for this number. So this is sort of summarizes what we just talked about. So here a captive or a sandwich 0 here, this number is significant because it's a sandwich 0. This trailing 0 here is not, because it's occurring to the left.